Microelectronic technology has evolved very rapidly over the last few decades.
Okay.
Even those of us who have grown up in the industry are repeatedly surprised at the capability of the technology and the sophistication of the products we're able to produce. Today we'd like to tell the story of the development of one of those products, Intel's 8386 microprocessor. I'd like to introduce Gene Hill, who was in charge of that development program, and indeed in charge of the program that developed the 8286 before it. And shortly we'll add to his credits the 486 as well.
So again, it was the optimization, continuing training. We've had a number of questions about the 386 design, and we thought it'd be interesting for you to hear those answers. To do this, we've collected questions from leading universities, professors there. And to help me with this, we have Pat Gelsinger. Pat's a Stanford graduate. He was one of the key engineers on the 386 and is currently the design manager of the 486 team. To ask the questions, we have our friend Alberto Sangiovanni-Vincentelli. He's a professor of electrical engineering and computer science at Berkeley. He's an IEEE fellow and emphasizes in CAD design. We've worked with him a lot as well as he's worked with industry, several other companies. Alberto, would you like to ask the questions?
Thank you, Gene. Now, today's our questions are organized in three parts. First part is related to product definition, and we're going to move into design methodology, and finally we're going to discuss the CAD tools that you have used in the 386 design. So the first question is, how was the product defined? How was the product definition process organized in Intel?
We started the process with a proposal of what a product might be like. The 286 architect made the proposal. He worked about 2 months defining this, and then we presented it to management and to a group of architects. It was unanimously decided that we should have such a product. And at that point, we selected a committee to do the product definition. They were charged with defining what the product would be. It didn't have a name at the time. The group was made up of a marketing specialist, which would understand what markets we would sell to, would understand the technical features of those markets. We had several architects, a logic designer.
Probably one too many architects.
One too many architects. Two was always one too many architects. And one of the architects in a previous life had been the compiler writer for Pascal on the 8086. We had a strong input from that.
Now, what kind of input did you get from the customers of your microprocessors?
We get a lot. We started out with a lot of input on what the 286 was. Customers are always very free about telling us what they think of our parts, what's wrong.
Yeah, particularly what's wrong.
Particularly what's wrong. Every time we have a design win or a design loss, we review it to understand what features we had, what was it that caused the win. So we had a big database of facts that we hadn't done as well in Unix systems, C-oriented languages, graphics, and we did a big study to understand that. As we went on with the definition team, we'd come to a point where we didn't have enough information within the group. It really wasn't clear, and we'd get several people together, get on a plane, and go see some customers. We'd select the customers based on did they have expertise in the field, were they a trendsetter in the field. And so we went to a big selection of customers talking about small parts of the machine.
So on an ongoing basis, too, throughout the process. It wasn't just like we went and talked to them once. It's like talk to them once, and then we'd run into another problem and go back out and ask them again and again until we think we had finally gotten to a point where everybody was most happy.
That's true. And as customers come in to complain about the deliveries on the last chip, they always want to talk about what's next. So it's an ongoing process.
Did IBM play any significant role in this definition process?
Surprisingly little. We did talk to them, but at the time, this was in 1981, the 286 had not been selected for the PCAT. In fact, the PC was an 8088 machine, and all this was just getting started. So the whole IBM thing began to happen while we were in the process of defining the chip.
A very important feature of the 386 is that it maintains backward compatibility with the previous products that you had, so that software designed for the other machine would run on the 386. Now, how difficult was to maintain upward compatibility with your design?
Well, the most difficult part was getting the decision that we should maintain compatibility. It wasn't obvious that, it was obvious we needed a 32-bit machine. It wasn't obvious that we needed compatibility with DOS until later on. And then when we decided we needed it, we went through a number of schemes trying to maintain compatibility and yet expand the chip upward. The breakthrough came when we stopped looking at the machine as a piece of hardware and tried to see what an operating system would like to have in dealing with 16-bit code, in dealing with 8-bit code, in dealing with 32-bit code. And the concept of running a 16-bit environment was really a breakthrough, that the operating system would spawn a 16-bit job and it should have this environment, or it would spawn a 32-bit job and it should have this environment. That then led to the breakthrough in architecting the 386 the way we did.
You were mentioning the role of operating systems in this development. Now, what kind of operating system did you consider while designing 386?
It became clear after much work and as the PC began to become important that we had an opportunity to pull together the DOS marketplace, which was beginning to have a lot of momentum, and the Unix marketplace, which previously had been two separate markets, two separate architectures, to pull those together. So the theme of the definition became how to have one platform that would run DOS applications and run Unix C applications equally well. And so those were the main things we homed in on for operating systems.
Among all the architectural choices that you have made while designing a 386, which one would you say was the most difficult to resolve?
The bus of the chip was the one that took the longest to define. As a matter of fact, most things were in place at least a year and a half before we made the final decision about the bus. We were attempting to maintain compatibility with other chips that Intel was doing. The definition, I think, had gotten a little out of hand. There were many features on the
Architects
bus.
had gone crazy with every different possible feature of multiprocessing, of fault tolerance, and the bus had become this behemoth of every idea that had ever crossed the books of computer architecture, it seemed.
So well into the design. In fact, it was a year before tape-out. We finally made a decision to break loose from that and do what is currently the 386 bus, which is much more simplified. That was driven a lot by looking at the cost of building this for a PC. That was definitely the most painful choice we made.
At the time, did you take into consideration the possibility of adopting a RISC architecture?
A little bit, not seriously. We were still learning how to spell RISC properly. It was a new idea that was just coming out, and we were much more impacted by other machines.
Yeah, much more of the classical architectures played a role. It really hadn't played that much of a role yet, even though typical computer architecture ideas were very important, focusing on the commonly used instructions, et cetera, which now have become much more embodied and understood in the RISC technology type things. But at the time, 1981, 1982, it really wasn't that big of a role yet.
Now, in one of the interesting parts about your design that was different from what your competition was doing was the aspect of cache memory and where this cache memory resided. So can you tell us something about it?
Well, at the time, our competition had a 256-byte cache on board. And of course, we had to outdo them. So we had a 512-byte code cache on board. And that was in the design for a long time. But as we went through optimizations, we couldn't figure out why to save it. It was very little performance advantage to it. It was a lot of design work. And we kept rerunning the traces, and we got terribly low hit rates. And as we worked on other optimizations, it was clear that bus pipelining and other things would have a bigger advantage. So we finally threw it out. And then we had to deal with the problem of how do you tell the customers, well, we don't have one. But the fact was we could run faster without it at that size. It was mainly limited by the amount of area that you could use on a chip.
It definitely started to hit some of the die size constraints. So here was a fairly costly die real estate option, which wasn't buying us all that much in performance when we really sat down and analyzed it. So we ended up throwing it out, adding bus pipelining, adding a fairly intelligent prefetch algorithm to get some of that same benefit back.
So the main point is if you have a feature on a chip and it isn't paying its way, you should throw it out.
Throw it away.
That's right. Caching is good, but 512-byte cache isn't really worth
It's a bit too much.
Yeah.
Now that we have discussed the product definition phase of the design of a 386, I would like to ask a few questions about the product implementation phase of the design. So I would like to ask you, Gene, before we get into the actual questions, if you could give us a little history about the design of the 386.
Certainly. We started the spec work, as I said, in 1981. We worked on that seriously for about 6 to 9 months. And at that point, we had a specification, and we worked for at least a year with a RTL, a register transfer level model. After that, we began the normal phases of logic design, circuit design, layout. We finally taped out in July of 1985, and in August we had parts. In September we showed those parts to the world.
Now, Pat, I would like to ask you, what were the design philosophy that you followed in the 386?
Well, it's sort of hard to say that there was one design philosophy. It sort of evolved with time. You know, we started out with a set of CAD tools, a set of understanding of the problem, and as we proceeded with time, a lot of the underlying assumptions started to change. A lot of the CAD tools that we could use, a lot of the process assumptions, a lot of those things started to change. So it wasn't particularly just one thing that we picked at one point in time, but it evolved with the entire process. Some of the things like standard cells, as we started the design, we didn't even really know what a standard cell was in 1982. But by 1983, when we actually started to get more into layout and standard cells became more of a known thing, we realized that this could really be a big boon to our layout productivity, which on a chip this size is a very important issue. And later on, when we got to the very end, we looked, and this was one of the key things that made it possible for us to get into auto place and route and auto wiring and so on. So it was a process that we couldn't foretell when we started the design in 1982, exactly how this is how we're going to do the rest of the design project. But as it went on, it was really fairly exciting to see that we actually could respond to the different design changes, merge different CAD tools, get different CAD tools created that we needed. And it was very much a changing philosophy as it went on.
During a design phase, in the definition, there's a lot of creative juices, and then it becomes less creative, and the engineers turn toward creating CAD tools or creating ways to do things. So it was a process all along of evolving the way we were designing it.
Some of the interesting things, like initially we struggled with the idea of doing a behavioral specification, for instance, in the design. And it's something, after you have a spec in place, the designers are just dying to jump in and start implementing and get this chip done. You're always thinking it'll take about half the time it really does sometimes. But rather than sitting down and doing a behavioral specification, we had the 286 in our pocket, and the designers were anxious we dive right into the implementation. So we never got this high-level behavioral specification done. We started with the written specifications, evolved those into the specifications for the units, the interfaces of the units, and then finally dove into the real design of the chip.
Would you say that in designing your circuitry, you traded off some performance to achieve faster designs?
Really true.
We were really, had a performance goal that we held very high. Maybe at the very end we shortcut it just a little bit, to get out the door. But otherwise, we set a performance target, and we worked very hard to meet that throughout it. The clock frequency, the clocks per instruction, and all those things. And we very only in minor ways sacrificed those just before we got out the door. In fact, we came back in most of the later steppings and fixed anything up.
That's right. In a given process technology, in a given chip, you reach kind of a knee where if you try to go faster, it just costs an enormous amount. We always tried to manage ourselves right in that knee, everywhere we were.
Right.
Pushing it 1 more megahertz doubles the design time.
That's right. That is going to be a problem for sure. Now, you brought up the point that you try to be in the knee of the process. Now, how well known and well defined were the details of the process when you started the design of 386, and how this knowledge evolved over the years?
The process design, the process development, and the chip design sort of went in parallel. So we had a pretty good idea of what the process would be. They sat down and basically did their process specification just like we did our architecture and chip specification. The two went in parallel. And they started out with some features that they thought they could include in the process, and as time went along, they started to see in some cases, the inoperability of them, or in other cases, they're just not useful. This is a wonderful technology aspect, but it didn't benefit us at all on the chip and was costly in the process. So there's optimizations going on along the way. Then we realized some of the difficulties of implementing some of the particular process features. So it was a constant feedback between both the process development and the chip development. This was the first major CMOS logic device at Intel and the first major CMOS process at Intel. So the two of them fed very well and occurred very well in parallel.
One of the reasons the design took so long is there's a tremendous amount of optimization. Optimization in the units, trying to optimize speed, trying to reduce the area. At the same time, we were trying to optimize the process against the logic chips that we were building. And that takes a good deal of time, but that's the only way to get a really good quality product.
And to have the fastest chip in the world, but only be able to manufacture one of them isn't a very interesting thing.
Not at all. Now, one of the interesting points that you brought up before was the fact that you had these functional units that you were designing. So how did you organize the partitioning of the design, and how the partitioning process changed over the years?
The partitioning, we started out with two things in our hand. We started out with the chip specification, what we're going to design to, and we started out with a 286 design, constantly referencing the two. So we took much the flavor, or much the concept of the 286 unit partitionings and applied that to the 386 unit partitionings. And a lot of things changed. We added paging and so on. And the resolution of this, we came up with about 8 units, and we put a circuit designer on each one, and an RTL designer or microarchitecture designer on each one, and they would partition their units, partition the interfaces between the units, and so they resolved how I'm going to communicate, whatever the communication paths would be between the units. And for the most part, the architecture or the micro divisions of the chip held throughout the design project, but there were these constant things going back and forth across the borders of the design. You take this logic, okay, I need this piece of logic to meet my speed paths. I don't want to do this. And especially at the end, it came very much, we had all these border wars when we were doing the final layout. We had all these topological wars, where this unit had grown and was very tight in its boundaries.
It was very much like the cattlemen and the sheep herders. There was a certain area, and the guy couldn't quite get in there, and he'd want a little of this guy's territory. So I had to get involved. Every Friday we'd sit down and I'd find out, how many sheep are in which areas, and I'd calculate the density, and then I'd give away a little of this guy's territory. But that happens all along. You don't know until you finish the layout exactly how much room it's going to take.
Yeah, but some of it's to optimize for layout reasons. Other of it, the logic minimizes better over here. Right. You improve speed paths by moving it topologically closer to this other part. A lot of that's really hard to predict at the beginning. So if we would, for instance, have finished the logic and send it off to another group sitting in another building, another state, to do the circuit design on it, that would have been a far less optimal design. But this constant interaction, the movement of logic to optimize day by day, and micron by micron in some cases, was very important.
If we had a critical path that was particularly hard to work, we'd put one person in charge of that, and then he would work and negotiate and try to work all of these things for this critical path, and a different critical path might have a different owner. So again, it was the optimizations, continuing trying to spend the time to make it work as fast as possible, instead of just trying to hurry the design out.
Right.
Worked very well.
Now, related to that, you indicated the speed of the chip. Now, what set the maximum clock rate? Was it the internal critical path or were the I/O path?
Surprisingly, it has changed with time. The first stepping came out, it was definitely internally critical path limited. And then we fixed everything that limited the path. And by the way, it was also sort of surprising that everything we thought was a critical path really wasn't. It's all the things that we didn't expect, that we didn't understand the parasitics of or something else that turned out to be critical paths. So we found all those in the first stepping, and then it became more I/O limited, so we had to retune our I/O buffers. And then the next stepping, it was really closer to the internal critical paths. So as steppings have gone by and as we've ramped our manufacturing, it's been a very close balance between the two, but there's never really one that was clearly always the critical path in the chip.
That's kind of by design. If you're clearly I/O limited, you have a bad design. You should be bandwidth limited, you should be internally limited, so you should be right there pushing everything to the wall as hard as you can go. So if we were slightly off at any particular point, that would become the limiter. So it was somewhat by design that we were right up there on the edge of everything.
Now, one of the big issues about design productivity is layout. So how much of that was done manually and how much was done with PLA generators and RAMS generators and regular design versus custom design?
The 386 has about 280,000 transistors inside of it, stuck in this little 1 centimeter square piece of silicon. And of those, about 130,000 of those transistors sit in ROMs, PLAs, RAMs, whatever. About 40,000 of those transistors are in random logic areas. And those were all done, as we've already talked a little bit about, by standard cells. And the final group is these data path ALUs, et cetera, and those are done by individual cells, which are highly optimized, minimizing parasitics, the last micron on them, the last femtofarad of parasitics, and arrayed and stepped and repeated to form our data paths and more regular structures.
You want those to be the critical limiters of speed internally. You don't want it to be some random path or something. So if you make those as fast as possible, then you can push the clock rate out. Right.
So these data path elements were about 100,000 transistors, and all in all, the individual transistors had to be sit down one by one, laid out, were about 9,000 transistors.
The rest came through replication of cells that were arrayed
by PLA generators or the standard cells that place and route.
Now, one of the most important issues, especially when you go up with speed and with the performance of these microprocessors, is packaging. So what kind of package requirements you had to fulfill with the 386?
Package requirements in the 386 were much more stringent than prior generations. First thing we had to meet our system design criteria and our I/O bandwidth, et cetera, we had to go to demultiplexed address and data buses. So that's 32 address, 32-bit data, so now we're at 64 pins. The biggest package before this was 68 pins, so we're clearly not going to fit in it. So we went to 132-pin ceramic pin grid array package. Another important thing was this is a CMOS device. CMOS is very dynamic current switching characteristics. So if you didn't have very good power and grounding to the device, it would just be so noisy that nothing would ever work. So we end up having 4 planes in the package, just like a little PC board inside of our ceramic package. 4 planes dedicated to power and ground, 2 each for logic and I/O. And then there's one final layer for all of the interconnect routing inside of the package to get it to the right pins.
For a time, we thought about putting decoupling capacitors inside also to be able to kill the noise spikes. We found we didn't have to do that, but it was a serious consideration.
But the package design was really critical and was highly optimized for the 386, much more than anything had been up to that point. Now looking back on it, it seems fairly simple and fairly straightforward, but at the time it was really quite innovative. I think another key thing that worked out was we really didn't understand the package modeling particularly well when we started into it, and we really over-designed all the aspects of that. And it's worked that our package was so solid that we've been able to scale the frequency significantly above the initial frequency and still have that package design very firm. We've often teased the designer who did the package design. If he would be a civil engineer building bridges, he would have accounted for 3 or 4 glaciatic ages. Very conservative, but at that very same time, a very important aspect of a CMOS design. We really over-designed that aspect.
Right. Now, among the things that people worry about in these days is testing. When you go up with a number of transistors, testing becomes really a limiting factor in the production schedule. So did you have testing in mind when you designed the 386?
Certainly. Surprisingly, some of the things that we were trying, again, looking back, they seem so simple and so straightforward, but at the time we really struggled with how, the importance and the right way to do it. We have all of these, we talked about the transistors and the RAM ROMs and PLAs, all of those are self-tested. We have built-in self-test, which exhaustively tests all of those, forms correct signatures. We use polynomial shift registers to form signatures of those, store the correct signatures on chip, compare them, and leave in a user-visible register after reset whether the part was good or bad. Besides that, we have built in a lot of accessibility to the internal state, such that when we're writing test programs, we can get in there and probe a lot of the internal state of the device, as well as some of the things like our TLB, our paging translation look-aside buffer. We have hooks where you can just go read, write everything in it. You can perform lookups and all these other things, which is real important for our CAM, content addressable memory, like you have in the TLB. Otherwise, the number of test patterns to try to test it are very difficult.
I would like also to ask you a question that I'm sure you will not have any problem, but did you have any problem during the design of the 386?
The bulk of the problems were associated with just the size of the design. This is the biggest chip designed in the industry to this point, biggest chip ever designed at Intel, and just across the board, the jobs were too big for the computer. The jobs were bigger than any CAD run for this particular CAD tool had ever been run before, so it broke it in all sorts of new ways.
Always overflowing arrays.
And we got into process limits, and it took the lithographic size possible to project and took it to its very limit.
As a matter of fact, the die size we have now is a 3% shrink. the die size we got was just that much bigger than the spec'd field of view
So
of the wafer stepper. So we just had to
bit.
squeeze it a little bit just to get it just inside, you know. So we were breaking the limits everywhere we went.
Computers, CAD tools, process limits, you know, package size, across the board we pushed it. You know, we're pushing technology on all these fronts to their, you know, to their limit, and just what we found too often, just a little bit beyond.
So we spent a lot of time debugging, but we were always able to recover and get the CAD tool to run just a little bit bigger, to get the size just a little bit smaller.
Buy maybe a new computer.
We did that too. A new plotter, all of those things.
So the next question is obviously, what CAD tools did you use, since you indicated that was one of the limitations that you had during the design?
I guess at the same time I call it a limitation, it was also an essential aspect of the design to allow us to do something this big. As going from the 286 generation to the 386 generation, the 286 we used a fair amount of CAD, but not in a very prolific sense. In the 386 we started to see the real necessity for really extensive CAD work. We, you know, at the 286 design, you know, a lot of the things we did manually, that by the 386 we just realized that the chips are getting too complex, and we had to spend a lot more time using CAD tools, developing CAD tools that supported our design. Some of the ones in particular, we did a RTL simulation, a high-level microarchitectural simulation of the chip, a real important simulator. You know, we didn't look so much to the schematics or the layout, what the chip was. This really defined the chip in a way that we could use, run test programs against. We also, you know, after the RTL simulation, we had MOSSIM, a switch-level simulator that was developed at Caltech, and we used it and had it extended. You know, took all those array sizes, made them a little bit bigger, and brought it internally. We also, later in the design process, procured a XiCAD acceleration engine, so we ran some of the simulations on there, and also later on used that for fault grading.
Right.
And going back to the testing question, we had, you know, late in the design, also we started fault grading the design, and fault graded it until we got to a satisfactory level of fault coverage throughout our test base. We also had IceBack circuit level simulator, you know, simulating those blocks, getting that last 100 picoseconds out of our ALU. We had the Applicon placement editing station.
Right.
That's right. And we used it industry standard at the time. We had C's internal schematic editor system that we used for schematics capture. We had HCVS, hierarchical connectivity verification system, which verified the schematics against the layout, verifying that all the transistors are there and all the transistors that shouldn't be there aren't. You know, we had later on in the process some other tools which did various queries and checks in the schematic, looking for dynamic logic, for charge sharing conditions, etc. And probably one of the most, a couple of most interesting ones and near and dear to your heart, where we had Espresso, the PLA minimizer, which came out of that little school across the bay again, as well as late in the process we developed in a crash course fashion automatic place and route system for the 386. We, up to this time, most of the place and route was at single level metal, and that was certainly not sufficient. We had this guy walk in and say, I can do a 2-level router in 2 months for you guys and it'll work perfect. And we laughed and he went ahead and did it. At the same time, we went and found the best place and route tool at the time that we could find, and that just happened to come from that same little school across the bay at Berkeley, the Timberwolf place and route. Put the two of them together, and between them we placed and routed almost every random logic transistor on the 386 was used that combination of tools.
We did a lot of tool development. A good 30% of the resources were working on developing a tool, checking out a tool, trying to find a better way to do things. So we were actively working our tools at the same time we were working the chip design.
But the design process is just getting more and more so a CAD design project.
Absolutely.
The two of them are being developed much more in parallel. One has a big role in the methodology used in the other. The requirements of the next generation chip have a huge impact on the next generation of CAD development.
Now, would you say that this 30% is going up or is going down over the years?
It's roughly holding constant.
It's holding constant.
Yeah,
so the effort in CAD is about constant.
This is just on the project team. Of course, we have people developing these tools. But these are guys using them, finding how they break, putting Band-Aids on them.
Right.
We're finding, like I said, the importance of CAD. We're picking up a lot more university CAD tools, looking at them much more thoroughly. Also looking at things going on in the CAD industry, an industry that's just sort of created in the last couple of years. So, and as well as we have a fairly large internal CAD development group doing CAD tool development. So the combination of the three we used in the 386 and later chips like the 486 were expending a lot more in CAD. And again, the methodologies and the CAD tool developments are developing in parallel.
Now, did you find that wearability was a serious problem, and how many planes did you use?
It's always a problem, and there's never enough.
Yeah, it's sort of interesting. The process is a two-layer metal process, metal 1, metal 2, and we have a poly which can be used for local interconnects. So some people say that's 2.5 or 2 1/4 or 2 3/4 of
2 1/8
layers of routability. But the chips that we're designing and the architectural constraints, we're moving 16 to 32 bits in the 386, and the clocks per instruction are constantly going down, so the parallelism, the pipelining, the design, the degree of which we're moving data back and forth is increasing, and wireability was a problem in the 386. If I had 3 layers, 4 layers of metal, we would have used all of them. Yep. But in future generations, due to architectural constraints, it's even becoming more and more of an issue. I don't see that we're going to, if I had 3 layers, I could find them used for a 4th and 5th and 6th and 7th and on, as well as some of the layers of metal become more important for power and clock routing as those things become more of an issue also.
It's a sizable manufacturing problem, though. Every time you add a metal layer, it's a big expense. So it's a constant trade-off. So again, we'd love to have as many as possible, but
again, a balance of what we can do architecturally with what we can manufacture in high volume.
2 or 3 levels of metal, I think, will be a good balance for the next generation or two.
Do you think that the process people are spending enough time in improving the metallization?
Well, certainly in the 386 generation, most of the process people were used to making SRAMs and DRAMs and so on, and didn't really understand what the constraints of a logic device were. They thought metal, you just used it for this couple of power buses around the edge of your die, and that was it. And it took us a while to work with the process people, training them how important metal was, because they thought that 1 layer of metal, which had inordinate spacing and dimension rules, was fine. And when we start shoving around 32-bit buses all over the die, it just doesn't make it. And that was a real struggle at the beginning. And now we have a lot of emphasis on logic technology development.
They were making a transition. In static grams, they were used to seeing a cell, and they knew the metal was going to be this way forever. And then they saw random logic chips, and we were getting into any possible configuration that you could think of. And, it was quite a learning exercise. I think both sides came up the learning curve a lot in that. But we've whipped 2-layer metal. We're looking ahead to 3.
Great. Now, did you do full chip extraction, since this chip was so big? It looks like this would be a big job to do.
Certainly was a big job, and we did full chip switch level simulations of the device, which was a real important aspect to find those last difficult configuration bugs, reset problems, X state problems, etc., as well as did a full bottom-up extraction of all the parasitics and tried to plug them all back into the circuit simulations. And that was another CAD tool that was developed near the end of the 386 and was really key to a lot of the performance verification aspects of the 386. And now, in retrospect, we're so much more sophisticated in how we extract parasitics that we would have resolved many of the later speed path problems, et cetera, up front in the early design.
Can you tell us something about what were the overall development costs in terms both of dollars and many years?
We've stated that we spent $100 million developing the 386, the process, the peripheral chips, the software tools that go immediately around it, design aids like the ICE support. The chip itself for the 386, at its peak we had 30 engineers working for a short time, kind of pyramid ramped up and pyramid ramped down. We also had about 15 mass designers at the peak drawing all the data paths and so on and so forth. About 70 man-years in total went into the chip's design.
It's certainly very substantial expense. But do you see this cost going up or going down over the years?
Unfortunately, it's not getting smaller quicker.
Next generation chips are about 1 million transistors. So of course the teams are growing, but the amount of stuff on the chip is growing. Actually, in terms of the function design, each generation we're getting more and more productive. It's just that the amount of stuff we put on a chip is growing faster than we're able to get productive. So the team sizes are growing very slowly.
I certainly hope that the CAD tools will be able to decrease some of these investments.
Well, it's not so much that the CAD tools are increasing the investment. They're the only thing that's allowing us to do so much bigger problems.
That's right.
So again, we went from 280,000 transistors in the 386 to over 1 million in the 486. So, I have, 4x the transistors, and the complexity of pipelining and the parallelism in the architectures, they're essential for us to do these much bigger problems.
That's right. And we were able to take a year off the design schedule that we had on the 286 when we did the 386. So it's the only way to do it, and they are giving us productivity.
Now there is a set of nasty questions, so
Okay.
get rid of that. The first question is, why did it take so long to develop?
We spent a lot of time in optimizations. As I said, we spent a year at the RTL phase, and much of that time we had a working chip. We were just trying to reduce the clock counts. We were trying to speed the part up. We spent a lot of time at each phase trying to optimize the die size. This is a custom design. We intended to sell millions of them. And we went in and spent the time to make it as fast as possible on the process and as small as we could. So it was primarily optimizations, a lot of optimization work.
Now, did the first silicon work right?
Close.
Almost.
Almost. We had one main problem with the first stepping. A big PLA in our instruction cracker, all our big PLAs were designed to be self-timed. In other words, a clock edge would start the AND plane, and then a circuit inside would say when to evaluate the OR plane. We borrowed one of the hot static RAM designers to do this so it would be as fast as possible. And he chose to leave just before the layout was done. And we dropped the ball. The things he'd assumed and the way the layout would be done weren't quite right with the circuit that was doing the self-timing. So part of the instructions would work right, and part of the instructions would go off and do Baroque things. And it took us a couple of days to understand what it was. When we saw that, we said, oh my God, what do we do? Because we can't go any further. And then you go into brain scratch mode. One of the fellows, there were several techniques suggested. One fellow came up with a technique that in very few layers could change this into just a static ripple through PLA. A stroke of genius, actually. And we cut some lines and tried to do that with a probe. It worked pretty well. And then we went off to change the mass set to make it work. That's a story in itself. Pat, do you want to tell how that happened?
Sure. The mass sets have chrome laid down on the quartz surface, and up to this point there was technology fairly well understood to get rid of chrome. But the edits we needed to do to the PLAs required both the addition and the deletion of chrome. You know, we had to move some lines, and this was never done before. Well, we got a lead on a new device, a new system that was being developed on the East Coast. So I grabbed the mask, hopped on a plane, flew to the East Coast, did the edits on this new system, you know, just hot off the presses, the first prototype they'd ever built. Did the edits, hopped on a plane, flew back, put it into fab, and the first samples from those edited wafers, or edited mass, came out the first working wafers, and we produced our first sample just in the nick of time to support introduction, you know, so that we could demonstrate something at introduction.
Was screaming in at the last minute, you know, with the part. One of the things we do is you make the wafer runs. If it's a checkout run that's so hot like this, we'll stop a few wafers at each step.
And check.
And then if you have something wrong, you don't have to go back to the beginning. And then you try to get very tricky about making changes, say, on the last layer of metal. Can I do this all on the last layer of metal? That way the turnaround time of checking it out would be shortest.
Yes. So how many tries did it take to get the design right?
That stepping that had the tweak on it was able to run the flight simulator program. So it was quite functional. We did have a B step, that's what we call it internally, which is where we speeded up a few nodes, went back and fixed the PLAs.
Fix the PLAs the right way rather than
Yes,
the quick
right.
way.
So that we could have the highest ultimate speed.
Yeah. And that was essentially our production stepping, which we went into mass production with.
That's right.
Now, when there is an issue about a latent bug that wasn't found in the initial steps,
oh,
can
yes.
you tell us about it?
I'll remember this for years. Well, in our circuit design, trying to have the chip run as fast as possible, of course, our ALU had look-ahead carry circuits. This is quite standard. But we got very tricky and patented a circuit that had groupings of 3 bits and groupings of 4 bits and 5 bits. We went through this great study to optimize the speed of the add. Within that, a look-ahead carry circuit is basically ending the carries off of several bits. But we had a decoding glitch, which is inherent in this kind of circuit that's clocked. But we didn't understand what exactly the worst-case condition was. What happened was we'd been in production for a while, and we had a very small yield problem. We put a screen in for it, and we had a small yield problem on one of the adds. And one of the experienced engineers who worked on the 8086 came on board to help us optimize our yields. He came on board on a Monday, and he talked to the main engineers and heard about this problem. Pretty soon he homed right in on this. And by Wednesday, he said, I think we got a major problem here. I don't think this is a minor yield problem. I think that if we do this function in the right way at 32 bits, maybe nothing would work, you know. Well, it got terrible around there after that. By Friday, he had demonstrated that indeed we had a 32-bit multiply case that would be a major yield impact. And that's bad because it limits what goes out to the field in our shipments. But the problem was we then had no confidence in the parts that were in the field. So we developed a screen and immediately told our customer base they could return their parts. More than that, we'll extend the warranties so that you won't have any problem with that. We tried to supply them extra parts, and we'd rotate them through. So people were nervous enough, we'd invited them to come in with their parts. You know, they could come stand by the tester while we'd retest them. And we went through a lot of handstands to get those parts back. Meanwhile, in parallel with this, we had to fix our production parts because we were beginning to spew them out of the factory with this bug in them. Again, we resorted to the same machine, and within a week of thinking that we had an important bug, we converted the entire line over to a fixed mask set. The fix was relatively simple. We just moved the switch point of the inverters that came off of these pairs so that...
basically increasing the noise margin to this potential glitch.
Right. So we moved it way away from the glitch, and the problem fundamentally went away. Yeah.
But it was really, a really important thing to resolve the issue. But then we just went out and said, we made a mistake to our entire customer base. Bring in your parts, we'll replace everyone. And in retrospect, I think it's one of the most ethical things I've ever seen a company do.
It was a lot of work.
Yes. Now you mentioned yield as an important factor, of course. Any manufacturing process has to worry about it. Now, can you describe us the manufacturing ramp and the problems associated with it?
That wasn't too nasty of a question. I usually hear this termed, isn't the 386, die size too big, and isn't that why you haven't been able to meet demand? So I assume that's the question inside, so I'll answer that one. When we began the part, each generation of silicon process, there's kind of an optimum die size. That's the die sizes which the cost per gate is the lowest. And the memory guys are used to this. This is where the cost per bit is the lowest price function. And we try to stay close to that die size. And in looking at Intel's history, it's always been the chip that's just slightly on the big side of that optimum that's important. And that's where we had the 386. We were trying to target it for that optimum die size. And of course, we made plans on how many of these we would sell, how the yields would come up. And we were surprisingly accurate on the yield side. Now, it's not to say it's easy to get the yields up. It was a new process and so forth. We had pegged that pretty close. We sampled the part. Some customers went to market, notably Compaq, and a few of the brave customers went to market with an AT-style box on the 386. And we began shipping those parts in rather large volumes. At about the end of the first year of production, we caught up with demand. I'd built a nice inventory in case things went awry. We had a yield problem or something, temporary glitch. And I actually was beginning to cut back wafer starts. The yield was coming up faster than the demand was going up. What was going on was IBM hadn't introduced yet. In fact, early on, you don't think anybody's going to use your part. Then it became, well, IBM's going to introduce a part, a new box using the 386, but it's not going to be like the AT. Okay, and then we sat down and we scratched our heads. Well, what's going to happen with demand? First of all, when is IBM going to introduce, and when is their volume going to take off? And when they make that introduction, what's going to happen to the market? Is everybody going to go, oh. We can't sell AT boxes. Okay, so one scenario would say that the demand would go down while everybody redesigned their boxes. Okay, what happened was completely the opposite. IBM, in April, May of a year, introduced the MCA box, or the PS2 box. And a funny thing happened. All of these vendors that had AT PCs immediately came out and said, we'll do a PS2 box. And then they immediately went into production with their AT box. And the volume doubled, and then it doubled again. The problem is, from the time you start a wafer until you ship the unit is about 3 months. And from the time we'd start wafers until they'd come out, the demand would go up. And you can't do anything about that. You can't roll time backwards to start more wafers. So we were working yield as hard as we could. We were trying to pull in the schedules, you know, so that we could react faster. We committed ourselves to double our yield every 6 months. We did that for about 1.5 years. But the demand would keep going up. It was like they knew what capacity we'd have because they'd increase the demand above that. Finally now, after in the fourth quarter of this year, we're meeting the demand of the 386. But to do that, we've had to bring up 4 different wafer fabs running the product. We've invested hundreds of millions of dollars in new equipment to be able to make more wafers. We brought up a whole fab site to ensure that downstream, even after this, we'll have more capacity. So it's been really tough. The problem was we guessed wrong, and where we guessed wrong happened to be on the demand.
Now, the last question of the day is going to be about the future. There is so much expectations out there about your future program, the 486. What can you tell us about it?
Oh, it's going to be great. You think the 386 was good?
Better than that.
Should see the 486. We're going to introduce it next year. Just like the 386, it'll be 100% code compatible.
We learned the compatibility lesson well.
We learned that. We know how to spell compatibility. It'll be about 1 million transistors. Probably the biggest surprise will be the performance. A lot of people, especially in the universities, don't think that you'll be able to achieve the performance that we've achieved on the 486. So that's the main item. We won't take backseat to anyone, no matter how they spell our architecture. It's going to be a great chip.
We're also excited by some of the new developments in design methodology and CAD tools that allow us to take on a 1 million transistor chip, even further shrinking design times, more architectural and parallelism and other things that really essential that CAD developments, the design methodologies, the process, so all these technologies are improving and evolving and allowing us to make the chips like the 486 bigger, better, faster. It just seems like there's no end to it.
So now that we heard about this exciting development of the 486, I would like to ask you a question that I think is going to be of great importance to our audience. And what would you recommend our students in our universities to focus on for a future IC and architecture designs?
Become good programmers.
Yeah, I think it's a much more combination of skills in IC design. Like we said, we've mentioned often during the discussion how important CAD is. Also that, the role of compilers, and the role of operating systems and the understanding of those aspects. Also system design. We're getting much more to as we've talked about in packaging, the thermal constraints of the design, also I/O, how fast you can drive your I/O. So system design, compilers, operating systems, CAD, which is much more a computer science type activity. And then of course your good electrical engineering things, your logic design, circuit design, process, etc. But really a breadth in their education is really important. Something I absolutely look for when we're interviewing new college graduates. Have they taken compilers, operating systems, all these other things, somewhat outside of the typical electrical engineering curriculum, but are really essential to a first-class microprocessor designer.
It's really critical.
What you are depicting is really a Renaissance man.
I think it's much more so that way than it has been past. But as we've said, we've just hit over and over again the role of CAD. I don't think we can avoid, this Renaissance understanding. Definitely a specialist in process or in logic or in compilers or in microcode. But definitely they need a breadth of this understanding to make all these trade-offs, all these optimizations that cross over these technological boundaries.
Well, with that bright look at the future for our graduates, we'd like to close. I want to thank Pat Gelsinger for joining us. I want to thank Alberto Sangiovanni-Vincentelli for joining us, and thank you.
Good. When you really get into this situation, it's amazing.
Yeah,
I just can't quite.
So this is
terrible.
I see an architect, because you think about the name, and then the name is all right, but then you forget what is important in the future about IC and architectural design. What would you say?
Okay.
That kind of stuff.
Let's go for it.
All right. So now that we heard about this exciting development of the 486, I would like to ask you a question that I think is going to be of great importance to our audience. And what would you recommend our students in our universities to focus on for a future